In this video I will compare these two radios on 144 MHz, 2 meters. As a first step I will test the noise figure of the Colibri. I am injecting a signal at minus 25 dBm directly into the radio. And you can see here on the S meter minus 24.2, and the error is too small to worry about. I can change this to minus let's say 80 dBm, and then I wait a little and the error is 1 dB, and that's within the precision of the signal generator. I can check this, the setting, it says 0, I click on it and it says minus 20, and now I read minus 79.7, almost exactly what the signal generator is suggesting. I switch off the signal to see where is the noise floor, and I can read it from the S meter, which I now know is fairly well calibrated, and it says minus 111 dBm. And if I click on this attenuator knob to go for the 0 dB setting, I read that the noise floor is at minus 122 dBm. The bandwidth is 1 kilohertz, and you can see the audio that goes into this instance of Linrad. We have 1 kilohertz of noise. Means that if the noise figure would have been 0, we should have seen minus 144 dBm in 1 kilohertz bandwidth, because Boltzmann's constant is minus 174 dBm per hertz. So this is what I can compute from that. The noise figure is 22 or 33 dB. And that's not too bad for a 2 meter receiver, because on 2 meters one would normally use an antenna mounted preamplifier, and giving it enough gain is not a problem. I'm using this setup to check reciprocal mixing and blocking. This notch is 60 decibels deep, which means that when these units are set to listen on these signal 144-149, there will be no noise added from this generator, even though it is set at a high level at some different frequency. And it looks like this. Generators, the notch filter, and the hybrid. Inside there is 70 ohm coaxial cable. The Airspy has a 2 dB attenuator in front of it, because I couldn't set the noise figure to be equal to the noise figure of the Colibri otherwise. But with this connection I have the same noise figure at this point. I mean at the output of the hybrid, both systems show a noise figure of 22 dB. So it's fair to compare them like this for dynamic range. I'm now listening to the Airspy, and you can see here on the Linrad screen, this instance of Linrad is connected to the loudspeaker output from both computers. And now I can hear the SDR sharp with the Airspy, and I have set the calibration here for the yellow track that shows signal to noise ratio to show 0. And what it shows is the power of the noise in this region, except for the red points here, compared to the noise, or the signal rather, that passes through this very narrow filter. So this is the standard procedure I use for this kind of things in Linrad. Now I switch off the Airspy and enable the SDR sharp. And I have to make sure that the frequency is exactly the right one. And I want to be at the center, the same place where I were before. And you can see the reading is now the same. It shows 0 because I have set the two radios to have the same noise figure. They also have the same bandwidth, very close to that. And the level I read is minus 106 dBm, and that is maybe a little bit surprising because I have 105 on the generator, but there is also some noise here. The signal to noise ratio for the expert SDR is not high enough for me to read the signal on the S meter. Anyway, I can now switch on the second generator here, and you can see it comes now with the same level as the other signal generator, but it is 60 decibels stronger. So when I change the frequency, now 10 kilohertz downwards, I know that there is no noise contribution from this box. And I increase the signal level until I see a degradation here. And I can see noise on the sides, but not very close. The loss is only 1 dB or so. So I add 5 more decibels. Well, now it's too much. I think I have a 3 dB loss at about this point. And this is for the Colibri. And the level I can record here is minus 23 dBm on this upper generator. And I mute the Colibri and enable the Airspy. And it's clearly more disturbed. You can see here about 12 dB. So I have to reduce the strong signal significantly. Something like this. And I switch it off to check. And you can see it goes up to 0. And on again. And the level that the Airspy can take is minus 39 dBm. And this is 10 kilohertz. I've set the frequency now 20 kilohertz below where I'm listening. It's a little bit hard to see, but we have noise peaks on both sides of this stronger signal. And it is a little bit more noise 20 kilohertz away than it is 10 kilohertz away. And that's very clear when we look at the signal generator. I had to set it to -44 to get back to a degradation of only 3 dB. So that's the Airspy, -44. And I switch that off and enable the Colibri. And you can see it's not affected at this level. I have to increase the interference significantly. Something like this. And that's -29. And now I go to 50 kilohertz away. 1, 2, 3. This is 50 kilohertz below, and we can see on the Colibri, I'm getting up on the shoulder of the noise peaks that surround strong signals. So I have to reduce the signal level here to get this standard loss of 3 dB. Means the reciprocal mixing noise is the same as the normal white noise of the amplifiers. Something like that. It is -35 dBm. And close that and enable the Airspy. And now the Airspy is not as good as the Colibri, but the difference is much smaller than before. So the Airspy is -47. And I go down another 50 kilohertz, 1, 2, 3, 4, 5, to be separated by 100 kilohertz. And this is the Airspy. And I switch off the signal, the strong one. And you can see it's not quite 3 dB. You can increase the level significantly. Here. So that's -40. Airspy -40. And then I switch that off and get the Colibri. And the Colibri is a little bit better, but not much. I increased the level by a couple of dB. Here, maybe even too much. I'm not doing this with very high precision. I'm looking for the grosser effects, but you can judge yourself how this is. Anyway, the signal level I have here is -38. And that is very close to what I have found on the Airspy. So, next I go down another 100 kilohertz, and then I can add more signal before there is a problem. Well, not quite as much as that. The noise peak is here, but I'm now, and the signal is down somewhere, and here's the noise peak, and I'm a little bit above it. So I can use a somewhat stronger signal. This is -34 for the Colibri. And here is the Airspy. And it is very much the same. So I write -34 for that one also. And then I go down by 300 kilohertz. 1, 2, 3. To become placed 500 kilohertz below the signal of interest. And you see, on the Airspy, I can increase the level a bit. Well, not quite that much. Something like this would be. And that is -27. And now I'm listening to the Colibri, and it's similar, although a little bit better. Aha, I had a spur here. I don't know the origin of that. Probably it has to do with nonlinear effects, I mean digital feedback on the A to D converter, because it varies when I change the amplitude. I'm not changing the frequency. So here is the result for the Colibri. Half a megahertz away, and I see -20 dBm. The point of 3 dB loss of signal to noise ratio that I showed how to get previously in this video, it converts to reciprocal mixing dynamic range like this. The noise figure 22 dB means that the noise floor is -125 dBm in 500 Hz. So this is the noise, the dynamic range in a bandwidth of 500 Hz, which is very often used to specify that. At some separation, that is 200 kilohertz, the two units are very similar. At a wider separation, the Colibri is a winner, but at much wider than this, I think the Airspy is going to beat the Colibri, because Colibri gets into saturation at about -19. That means 106, and that's the limit. But the tuner in the Airspy has the ability of rejecting signals that are well outside the IF passband. And then one has to set, you can see here, I have done this test in sensitivity mode, but if I switch for linearity mode, the tuner is going to be used better. But for wider separations than this, the clever radio amateur will insert a filter to get rid of things that is causing problems, if he would use the Colibri, or also the Airspy. Anyway, at very close range, the Colibri is very good, but it has this noise hump. So that's the reason why it is no better than the Airspy at this separation. But 20 to 50 kilohertz, the Colibri is significantly better than the Airspy. And that should be expected. And I think this noise hump that degrades performance here should not be expected. I have removed the notch filter and sent two equally strong signals separated by 10 kilohertz into the two receivers. And just look at the screen with the loudspeaker switched off. And I step up the level in steps of 5 dBm. And I can look here on the Airspy. Here we see problems, and here are more severe problems. So here is approximately the maximum signal level for the third order intermodulation at close range, and that is minus 45 dBm. On the Colibri I can go up more in signal level. And not until here I see the intermodulation, and it is much weaker than the noise sidebands. And here there is saturation. So IM3 is not a problem with the Colibri, but here is what you see on the Airspy at minus 30 dBm. So this, I think, is enough to see the big differences between these two radios on this aspect of receiving.